Welcome back to the video. So today we're going to talk about AVL trees and in general the AVL algorithm. AVL stands for the people that made it. I actually asked that as an extra credit question on the final. I'm not going to ask it again. I don't even remember the name, but I think they're Eastern European.
Is it AVL?
AVL.
AVL.
Yeah, Google it. Read it out loud if you find it. It should be on the Wikipedia page.
Invented by Gregory Adelson-Belsky.
Yeah, Adelson-Belsky.
Adelson-Belsky and Landis.
And Landis. So there you go. So that's multiple people here. So imagine that would have been your extra credit question. But that semester I did say the name in class. You know. So anyways, just so you know, in case you're curious where the AVL name comes from. And so the introduction to AVL trees I kind of gave you before, but I'll rehash it. And that is the fact that when we're going to go back to thinking about binary search trees now. So not just binary trees, binary search trees, meaning that if we have a root node, anything on the left of that is smaller or equal, and anything on the right is greater than, smaller or equal than the root for both of these, right? So if this was a 5, this would be a 6, this could be a 4. Actually, here we'll say it's anything less than or equal to 5, and here it's anything greater than 5, right? So you can call it X and Y, so we don't have the same one. Now, just like with sorting, what do you define as something greater than or less than? You have a sort function for that. So if you're talking about sorting like words, then it should just be alphabetical. But if it was something like 10,000 chips, which you will do, then you use the same sort function that you used before, right? So you take into consideration uppercase and lowercase and so on, right? But ultimately, as long as you have a function that tells you whether something is less than, equal, or greater than, then you can use an AVL tree for that.
You just did the wrong symbol right there for greater than 1.
Yes, thank you. I'm glad we caught that. Otherwise, they go in the video and I have to put comments. Great. Okay. So, what was the problem? Because remember, as we're inserting this, if we want to insert n elements, it's going to take n time. We just have to insert it, right? Not quite. Because when we insert one element, it's not just going to take one comparison. We have to find out where on the tree it goes. So if we have a tree like this, in the worst case scenario, we have to compare 1, 2, 3, and 4 times. And then after that, it might go here or here. Best case scenario up here would be something here. 1, 2, and then here, right? Whether it's inserting or deleting, that would be kind of the possibility, the range of comparisons that you may have to do. So what we said was, if we have a tree of height log n, which we consider valence, then it would only take log n time per insertion. And if there's n of them, then it's just n log n, right? But if we have a degenerate tree where the height is in balance or the height is not log n, then it's like a linked list, and each of them could potentially take n time, and it's basically n squared, right? So we want to have a balanced tree. And AVLs are going to be the way that we can achieve that. How? As we start inserting things, we're going to monitor the height of the tree. And if it ever gets unbalanced, meaning the height is between the left and the right are greater than 1, then we will perform what's called rotations to fix that. So without showing you how the rotations and everything work, let me give you an example of that. So suppose we have nothing in our tree, and we're going to insert the numbers 3, 1, 2, okay? 3 goes at the root because we have nothing, and then 1 is less than 3, so it goes on the left, and 2 is greater than 3, so it goes on the right. How do we check the current height of the tree? Well, if you remember what I showed you is you start out with zeros at the leaf nodes, and you work your way up. Every time you go up a link here, you add 1 to the biggest number of the two. So here they're both zeros, so it becomes a 1. Over here they're both zeros, so here becomes a 1. Suppose that we then go ahead and insert a 4 or a 5. Let's do a 5. Okay, where's the 5 going to go? Actually, nobody said anything about the 2 being on the wrong spot. Yeah, we'll call that a 4 then. There, problem solved. Okay, so anyways, so we suppose we insert a 5, okay? Where's the 5 gonna go? To the right of the 4. Okay, after we finish an insertion, we're gonna check our height. So let's see what the height looks like now. We started 0, 0 here. This height gets updated from 0 to 1. And then now we take the highest of that, which is 1. So this gets updated to 2. The difference here of all the sections in the tree, notice that nothing on this side got changed, is still okay. Because here we have 0 difference, here we have a 1 difference, and here we have a 1 difference. As long as that difference is less than 2, or other way you can think of it is as long as the difference is 1 or less, basically we're okay. Let's insert a 2, since we had a 2 before, but this time in the right spot. Where's that going to be? That's right. So how my height's going to get updated as? Well, this height gets updated to 1. And then because you have a 0 and a 1 here, then this gets updated to 2. And everything is still balanced, okay? Let me redraw the tree now since it's getting kind of messy. Okay. So we have 0, 0, we have a 1, 0, and 2 because we took the biggest number there. And here we have 0, 0, we have a 1, 0, and 2. Okay, let's go ahead and insert now a 6 and a 7. Actually, 6 will be enough to see something happen here. So we're going to insert a 6. 6 is going to go here. Okay, notice something here. We have a 0, 0 here of height. This becomes a 1, and then this becomes a 2. That difference is more than 1, right? It's 2. This means the subtree here is unbalanced. So this whole thing is unbalanced right here. It's starting to become a degenerate tree per se. And so what we will learn to do is to rotate it. In this case, what this is going to look like is we are going to still maintain the binary search tree property and try to make the least number of changes possible while maintaining both binary search tree and decreasing that height difference to maintain it under 2, so 1 or less, so that we can have that log n height of the tree. Well, it turns, or almost log n. Sometimes it might be a little bit off. It's not going to be exactly, but what happens here is, I kind of, the best example for this is take what we have now, take the 3, take the 1 and the 2. We're not going to touch that side. We're going to touch what's here. So here we have that 4, 5, and 6, okay? So what I'm going to do is imagine that these are held by gravity, with a string or something. And instead of grabbing it from here, I'm going to grab it from here, and I'm going to pull that up. So I don't know if I can do that here. I'm going to pull it up like that. And this link over here, that was this, at the 5, it's going to go up like that, right? Can I visualize that? And then the link over here that was pointing there, in this case, it's just going to contain still point to there, right? So, like that. Does that, can you see that? Does that make sense? Right? I'll do replay. We are pulling the 5 up, and so this is kind of swinging down here, essentially. And now, this was, we'll shrink the size of this. Actually, here, we'll just redraw it. We have a 5, 4, and 6, and this was all linked here, right? That's where it was originally linked. So now, we're just going to put it back in there. So the tree's going to look like this. Not a 4 there anymore, but a 5 and a 4 and a 6. And you can already see how this, compared to the tree before, this looks a little bit tighter, We squished the tree, the height of the tree, right? We crushed it. And we are trying to maintain that log n height. Log n height meaning here we have 1, 2, 3, 4, 5, 6. 6 items, yeah? And so what's that equal to approximately? 3, let's just say. And so our height, if we count from this way, 0, 1, 2. So it's about that, right? So It's within range. Ultimately, it's going to be plus or minus 1 or 2, but it's still going to maintain it as long as you do this, okay? So this idea of performing rotations is the heart of the AVL tree algorithm. So before I go any further, I'm going to go ahead and write down here, and I'll also put it on the projector while I write it down in case you want to write it. But I'll copy it into the notes here in a second. So, in fact, I can do the picture thing, can I? Is that gonna mess with the recording?
Find out.
Yeah, we'll find out.
You can't take pictures of it.
No, you can't?
I don't think so.
Okay, then let's not break it. So, anyways. So I'm gonna write that down in here, but you can see it already. So we have 4 rotations that we're gonna talk about. And these are actually 2 of them here. I think I have a smaller one where you can see them a little bit more compressed. These are from Geeks for Geeks, by the way. If you want to just get it from there. I don't know whether. Here, I will just make them. So, I think it's easier if you see what I'm drawing it, because I can explain it probably. Yeah, let's just go with that, actually. So, first we're going to see the one that I was showing you. We have a situation where we have something of this format, XYZ. XYZ representing any values that are in the binary search. And what that is going to become is XYZ like this. And so here's the thing. I show you a simple example like that, right? But there might be children involved. Like X, Y, and Z may have children. Where could they have children? Where there could be a children here, which we'll call this 1. There could be a child here, which we'll call 2, child here called 3, and child here called 4. So when you do the rotation, and you're coding the rotation, because that's your assignment 8, where are you going to keep those at? Well, it turns out that in this rotation, these children don't get modified. However, and then X left children doesn't get modified, but this one gets modified. Notice how it's going to go from, and in fact, maybe I'll highlight that one because of that. It goes from being a child of Y, a left child of Y, it's going to become a right child of X. And that's always going to be the case, always. So that's one of those things you just have to you don't have to learn it, but it makes sense as well. But you could also just hardcore memorize it, doesn't matter. Notice why that's the case, because X, anything to the right of X is bigger than X, right? So this 2 here is bigger than X, but is less than Y. That's what it's saying. Over here in the right X picture, that still applies. The 2 is bigger than X, but is less than Y. So they both represent the same thing, and that's why it goes there. So if you forget this during a test or something, you can deduce it like this. But it's also, nice to remember it. So we call this type of rotation a left rotation. And I have even a comment here saying, think of it as if we're holding the Y by a string and sort of holding it up like that, okay? So if we go ahead and mirror this, in fact, wouldn't it be cool? We still haven't figured out how to mirror pictures, have we? Nope. Nah, that doesn't work. Oh well, we'll redraw it again. But basically, the mirror of this applies as well. Actually, it doesn't quite work out as a mirror because of the letter, so either way. If we have something of this format, Z, I don't like that Z, it looks weird. Z, Y, and X, you can rotate that into X, Y, Z. Like that. And your children, 4 and 3, these children remain the same. These children remains the same. We'll call that 1. The only one that's going to change is, again, the y. Again, this is saying it's greater than y but less than z, which holds for both examples here. Okay? So, I see some scared faces. Yes?
How is 1 greater than z, but 2
No,
less than z?
Yes. Don't think of the numbers as being like actual values. Think of them as variables. I just didn't want to use letters. But just, yes, don't think of them as numbers. If there were numbers there, then yes, it would look backwards, but no. I put numbers because I don't want you to get confused with the x and y and z of the tree. But yeah, just think of them as identifiers or something. Other questions of that? Okay. So now we're going to see the other 2 rotations. The other 2 rotations that we can have are what we call double rotations. So let me introduce you to an example where you run into that problem. Here we go. And then, in fact, let me introduce you to a right rotation, first of all, which is this one. A left rotation you saw. It's basically, if you do something like this, 1, 2, and 3, by the time you get to 3, there's already a problem here at the parent, so the child is the one you're going to pull up as a new root, or the new parent, right? Okay, what's the other example where you can get a right rotation now? Because this is more like a left one. So this is left, now we're going to see right. Suppose that you're inserting the values 3, 2, and 1. 3 gets inserted, 2 gets inserted there, 1 gets inserted there. By the time that 1 gets inserted, you can see here, difference of greater than 1. Then you get your rotation, which pulls up to 2, and you get that. Suppose that they had children, since you want to see maybe an example with children. So suppose that you had a tree like this. So you were inserting 4, 2, 3, 1. Yeah, okay, so 4 gets inserted, 2 gets inserted, 3 gets inserted, and then 1 gets inserted. So far, we're okay, right? No, we're not okay at that point. In fact, before even the 1 got inserted, were we okay there? 0, 0, 1, 0, 2, 0. That's when it breaks, right? And the thing is, after each insert, you want to check if it breaks. You don't want to keep going if it's already broken. So, okay, you have a situation like this. How do I rotate this? You're thinking, well, if it makes it easier for you, if a child doesn't have any, if a node doesn't have any children, go ahead and pretend like it does. Give it a value. Give it like a, let's give it an A. All right, and so now that it has an A, then I can perform my rotation. So if I look at the algorithm for that rotation, make it smaller. So if I look at that algorithm, it says that 2 should be my new root. The 4 should be the right child of 2. And then the A is basically the X in this case, which is of course not a real node, but we're going to put it in anyways like that. Where's the 2 going to go? Or sorry, where's the 3 going to go? to the left of 4. So you perform your rotation, and you're like, well, I rotated. Everything must be okay, right? Is it okay? Yeah, 3. But is it okay? Because remember, this is an imaginary node, so we can just get rid of it now. Did you fix the real problem? No. You sort of like mirrored it, right? So you're like, oh no, what do I do now? So you're like, maybe I should perform another rotation again. Maybe it'll be okay, you know. If it doesn't compile, maybe if you recompile it, it'll be okay. Okay, let's go ahead and give that a try. 2, 4, 3. Let's just have our imaginary A there so that we can rotate it. So then that becomes a new root. The 2 goes over here, and then the A goes over here, right? Yep. And then where does the 3 go? And then you erase that, and you're like, that's what I started with. So what do I do? Panic mode activated in the test, right? So there are some cases where doing a single left or a single right rotation, if you do a rotation twice, you're gonna end up with the same thing because you're mirroring it. So that's why we ended up with the same thing. But here's the thing, sometimes there are cases where doing a left rotation or a right rotation are not gonna fix the problem of the height, such as this case. So therein come the other 2 rotations that I'm going to show you that can fix that problem. So that was our original one right here. But before I show you the rotation, just from a sort of a conceptual point of view, what do you think I should do to fix this?
Move the 3 to the top.
Move the 3 to the top
Like the,
as a root node, you mean?
it's like the root node, so you have the 2 on the left side and the 4 on the right side.
Yes. So how do I get to that algorithmically? Okay. Well, I don't expect you to know, because otherwise, why would you be sitting here? So what you're going to do is you're going to mirror the little children here. So you're going to think of this as the grandparents. This is the only time, remember I told you the word grandparents not really used except for like maybe AVLs? This is the time. You're going to look at the grandparent, which is the one that's unbalanced. And you're going to look at the grandkid and the parent. And you're going to flip the parent and the grandkid. So from like this, you're going to make it that. And if you do that, what do you end up with? That, which then we can just perform a simple rotation using this one. And so we can say, well, I mean, I don't know if I had to go through this, but I guess since we're just starting it, might as well see it, you know. You do that, which you end up with what you were looking for. So even if you don't remember rotations, you could probably get it solved in the test. Where it becomes scary is if there's a bunch of children around that, and then it's harder to visualize that the rotation is happening. And also when you're trying to code it, you can't just be like, yeah, you just do things. No, you have to like systematically say what happens. So what you do is you're gonna mirror the grandchild, and then you're gonna perform a single rotation on that. And that will take care of your problem. And those are called, sometimes some people call them double rotations. Some call them like left-right or right-left rotations. Because technically, how did I do this weird rotation here, this little mirror? Let's go ahead and replay that action. All you do is you throw in your imaginary A, and now you consider this subtree. And you can still use that same, so technically you don't need to memorize 4 rotations. You just need to memorize 2 and understand them. And then you don't really memorize, you don't need to memorize 2 rotations. You just need to memorize 1 and remember that you can mirror it. So really this is it. If you remember that in the AVL, in the test, you should be good to go if you had like 5 hours to derive everything else, right? But you don't, so you might have to practice a little bit beforehand. Because using that, 3 goes up here, 2 goes here, A goes here. And then if there were any children, like if this had a children called, we'll say L, K, and there's obviously nothing here, but we'll say J, I, then basically here we get L. What will be here? K. And then Ji, right? If we had any children, but we don't. So of course, at this point, we can just eliminate that. All the imaginary stuff, and all we're left with is just that. So all that worked for that little mirror. But I'm just showing you the systematic way of doing it. Of course, you don't have to think about any of that. And then of course, we still have the 4 coming out of that. So then, you perform your rotation, and you end up with that. So now that you hopefully understand it, I'm still going to show you the sort of the variable method, so the algorithmic way of doing that. Maybe I'll put all 4 together. So I'll copy these down, and I'll put the other ones beneath in case anybody's like printing these out sometime or something from the PDF. Plus, I might copy and paste that into tomorrow's lecture. So the other cases are going to be, if we have something of this form, Z, Y, X. And so what you will do in this case is first, you're going to rotate it into Z, X, Y. And then you're going to rotate it into X, Y, Z. And then let's keep track of our children, because don't forget to think about the children. Like that. The only tricky one that moved around was the 2. It changed parents. The X and the 3 and the 4 and the 1 are still the same spot. And then one more time, once we do the other rotation, then the 3 changes spots. So between this rotation and this rotation here, that changes spots. So, I mean, when you're coding this, if you want to be lazy about it, not lazy, it's just smart, you can just code one function that does a rotation, right? And then you can call that function twice on the right parameters to perform any other rotations, right? Maybe code 2 functions, one that mirrors it. But don't you already have a mirror function? Yeah, you do. Yeah, so you can use the mirror function. So you just have to code one function that does a rotation, and then basically fiddle with it for any other rotations, like call the function twice to do the double rotation here that you're looking at. Or you can just hard code a rotation here, because this would be called a left rotation here, right? And then this is a right rotation. Do you see why it's a left rotation? Because we're rotating Y, X, and then that imaginary A. That's really why. In fact, maybe I highlight it with yellow. You can think of the 3 as the one that you're rotating. And then the right rotation in this case is these 3 coming down, right? So that's where the name left, right comes from. So we got a left rotation, right rotation, and then this is just called left, right rotation. How you feel about that? Let me go ahead and put the last rotation in, and then we will just do examples forever. So that's just basically the mirror of this. So it's going to be called the right left. So Z, Y, X. Let's put the children. 1, 2, 3, 4. And so that is going to become Z. Basically the grandchildren out and the parent rotate. I'm doing my best to try to make it neat. Okay, and I guess I'll highlight things again. So any children that got changed are going to be, it's always one children if you think about it, that gets moved around. In this case, it's 3. It should be the mirror of the one above it, right? 3 got moved around. All the other ones are actually in the same spot. And what I mean by move around is, in your function, you're gonna have some sort of pointer that got changed. You know, it's no longer pointing from X, from your left pointer of X is now pointing to Y, and then the right pointer of Y is now pointing to 3, and so on. So those are all the pointers you get to move around. That's why this assignment is hard, because what happens when you move pointers? You screw up and then it crashes, right? I don't know why that got changed. Anything else got updated? Nope. That's it, right? That's the only one. And so again, if you want to visualize why this is a right rotation is the one that goes like that. So that's technically you're rotating the 2, the X and the Y here. And that's becoming 2XY here, that little triangle. And then why this is a left rotation? Well, that one is more obvious. You got that, which becomes that. And there you go. There are your 4 rotations. They are your like Bible for AVL trees. If you know them by heart, then you can do them faster. If not, you can still derive them. It just takes a little bit of time and understanding. And I really, that's important. I care more about you being able to understand how they got developed than just hardcore memorizing them. But it does help with the speed. I don't have them memorized by heart. I mean, it's getting obvious to just remember one of them and the other because it's mirrored. But like, I don't remember where the children go for this one, for the right left. I just have to like do this by hand first. And what I could recommend in the test is do it on a piece of paper and then use that as a reference to get everything done. So any questions on the rotations right now? So now let's just, for the next half an hour, do examples so we can get a feel for it. So I think I have some semi-curated examples that will generate some stuff. I don't have the way that they got inputted though. We'll come up with them. Yeah, go ahead.
So say like you have X, Y in like this last example, and you don't see like children right there, but you still want to do like a left rotation on it.
So you draw like a fake children basically.
Yeah. Do you temporarily make like a node and just have it be like nothing in it?
Yep,
Okay.
pretty much. That's my A node that I'm using, but yes. Okay. Good question. All right. So, yeah, we'll just kind of, I'll insert, first of all, would you like to do numbers or letters? Nothing? Letters. Okay. I mean, I could think of other things, but then I can't think of like sorting them, you know? Because someone's like, do shapes. I was like, oh, no. So, letters. So, let's just go ahead and try to insert J and see what happens. Or I know what we'll insert. Let's insert Corona. So we'll start for the C. And here duplicates are okay because it's a binary search tree. We know how to handle that. We're okay. So far we have nothing. So now we have a root. The algorithm for inserting is after you finish inserting, you check the tree. You will notice something about those checks in a second once the tree grows a little bit. But for now, 0, 0. We're good. Okay, next let's go ahead and insert an O. And you guys double check, make sure I don't put it in the wrong spots. O goes there. Okay, you do your checks for height. 0, 0. This gets updated to a 1. Now we're gonna insert the R. But before I do, I want you to notice something. When you insert something into the tree, you're only gonna, and half is a misleading word, but you're really only gonna check one side of the tree for the height updates, right? The side that you insert on. Because if I insert stuff on this side here, it's never gonna modify that 0 there. You have to still check the 0 against whatever you get here, in the 1, but it's never gonna modify it, right? So when I'm doing my checks and I'm propagating the checks up from where I inserted, you propagate them up from there, from the leaf node that you just inserted. You don't need to run them checking the entire tree. That's just a waste of computation time. Okay. Get rid of the dotted line. There we go. Next, we're going to put the R. Where's the R going to go? Yes. Okay. 0, 0. That, of course, updates this 1. And then that, of course, updates this 2. Okay. As we were updating, we check as we go, right? Here it was a difference of 1. So, we can say diff is 1, diff is 0, diff is 2. Warning. That's bad, right? That's when we gotta rotate. Of course, I think I mentioned this, but if I didn't, you pick the biggest number of these two, and that's the one you feed up the tree. That's why you pick the 1 here and not the 0. Okay? Making sure that I mentioned that. So, because we know that this is the first spot where it's unbalanced, what you're going to do is, even if there was something above this, you're not going to mess with that. You're only going to mess from there down, which in this case is the root. And so when you're picking which rotation to do, you have to see the structure of the tree, or you can just try rotation and see. Because remember, if you try a rotation that doesn't work, you just do it again and you get back to the original one, right? So you could just call rotations and hope for the best. But you could also analyze and see which side is heavier than the other one. In this case, the left side is the bigger one, right? That's the one where it's heavier per se. And so if we go ahead and look up here, the left rotation kind of alleviates the left side when it's heavier. So that's one way that you could identify that as being the one that you should call. So anyways, you call a left rotation. And this becomes COR. Cool? We can keep going now. So we got Corona, and we just inserted the R. So now we're going to insert the O. Where's the O going to go? Anything here is less than or equal to, so that means it goes to the left of that. But then it goes to the right of the C, so it goes there. Yeah? Okay. 0, 0. And by the way, after you perform your rotation, how do you check if the rotation fixed it? You just check the height. which by the way, before we inserted that, would have been like that. And then you would see that that's okay. And by the way, it's possible that up here, it might have broken too. It's possible. So you don't just finish there. You go back and you finish checking the rest of the tree. But there's nothing now. So we'll see that once the tree grows a little bit bigger. Okay, so we inserted the O though. So now this gets updated to a 1. And what does this get updated to? A 2. Are we okay? Yeah. The N is next. Let's make another copy. Where's the N gonna go? To the left of O? So we got 0, 0. That gets updated to a 1. This gets updated to a 2. Look at that. I'm so happy we got a double rotation now because we can see that, right? I didn't intend that, so that's cool. So again, which side is heavy technically, left or right? I think I said left before, right? I was looking at it backwards. So I guess flip the wording of what I said. If the right side is heavier, you call it the left rotation. Yeah. I'm left-handed and I flip that often. So in this case, the right is heavier, so you want to call a left rotation. But what happens if you call a left rotation? You're going to end up with, well, not with that ordering of the letters. You're going to end up with that structure. But it's going to be like that, which doesn't do anything for us, right? So if you perform your right rotation, or sorry, your left rotation, and you get this, and it doesn't help because you go ahead and you check the height. Would you like me to show you the rotation, I suppose?
Yeah, sure.
Okay, let's just do that. So systematically, you're like, okay, the left is heavier, the right is heavier, so I'm going to call a left rotation. So you're like, okay, let me call the left rotation. But you can't really do it because you don't have a child there. So that's when you throw in your imaginary A, which for now, since we have, yeah, we'll do lowercase, that way we'll still know that it's imaginary. Or temporary per se. So now it looks more like a proper left rotation, as you can see there. And of course, this is hanging from something, but you know, whatever that is, it's still going to be hanging from there. But now instead of the C, it's the O, right? And then we have the A here, and then the child. So this is, which child is that over here? That is child number 2, which ends up there, right? So child number 2 ends up here. And then you go ahead and you recheck your weights. 0, 0, 0, 1, 2, over here 0, 0, 1. Oh, what did I do wrong? Or what did I not?
You didn't take out your temporary?
Yeah, I didn't take out the temporary. So really there's nothing there at that point. So that's a 0, right? Yeah. I was like, whoa, I fixed it. That's scary. But no. But once you take away the temporary, and then you go ahead and rerun the height check, and then you see that again that you didn't do anything. And not just that, but now it's left heavy instead of right heavy. So then what does it say? Well, if it's left heavy, we're calling the opposite one, right? So we call right. So then we call right again. Let's just go ahead and do that. Temporary on. So there's our thing. That's going to become CAO, and then end over here. If you want to check that, you can see here the 2 became there, as you can see. And then get rid of the temporary before you measure, and then go ahead and recheck your heights. 0, 0, 1, 0, 2, 0. And that's when you're like, well, I came back to the original state. If you perform two rotations and you're still back to the original one, or you're just not making progress, that's when, and this is the good thing about this, okay? Because think about it, when you're doing the rotations, you don't want to have like a backup copy of the original one. You can just call the rotation to fix it. If you rotate it once and it doesn't fix it, you try rotating it again based on the algorithm, and it still doesn't fix it, odds are you just ended up back with what you started with. At that point in your code, you can be like, okay, I will now attempt a double rotation, which is a left, right, or a right, left. So which one do you pick? Well, you have this, so we'll copy this down. And we're back to this, right? Because we double rotated. So we're back to the original one. You have this structure here. Okay, that works. You have this structure here, and you're seeing that the right side, and make sure I don't get them wrong, the right side is heavy, right? That's your right-left rotation. So call the right-left rotation if your right side is heavy.
So isn't it the other way?
Isn't it? It's built. Wait, I don't have it drawn. No, I have it CON like that.
From what part though? The very top root or just like?
You start counting or you start looking at it from where it breaks, and it breaks at the C. So that's why I squared it out. So from there you can see that it looks like this one, ZYX like that. Look at the yellow. Well, that yellow didn't come out as well. I don't want to use another color. Look at the ZYX and how that looks like that. In fact, maybe I'll draw a little tiny version of it here so you can see it without all the marks like that. If it looks like that, I know it's tiny, but when you see it on the PDF, it'll look nice. Then that's what you use that one for. And for this one, is if it looks like this, ZYX. And then maybe we'll do that one for this ones too. Well, here it's easier to see. And let's put the weights as well. So here you can see the weight on that side is heavy. Here you can see nothing because it's too tiny. Let me try to move this a little bit up. So you can see here that this is 0 and this is 2. Can you see that? Okay. And then here you have X, Y, Z, and here you have 0, and here you have 2. And on this one, you can see, I'll write them big, but they're the numbers, they're the weights. You can see the left side is heavy, and here you can see the right side is heavy, okay? So that way I can, the reason why I care about all those little things is because those are little checks you're gonna do to see which rotation you call in the code. It looks obvious to us when we're looking at it because we have the picture, but the computer doesn't see the picture, right? You have to tell it numbers that I can quantify. So ultimately, because the right side is heavy, which one should we call? The right-left rotation, because the right side is heavy in that. Okay, so the right-left rotation is consisting of two rotations, a right rotation and a left rotation. The right rotation is not going to be performed on this one, though. It's going to perform the child of that, meaning the O. So we're going to look at that first, just this part. We're going to ignore the C for this part. And we're going to do that rotation, that right rotation. How do we do it? We add our imaginary node, and then we go ahead and we perform the rotation. We are done with the rotation. Let's plug it back into our thing. That looked like Nevada. Actually, no, that's backwards from Nevada. Okay, so we are plugging back in the part that we removed, which was the ON. And we're plugging it back in with what we just got from the rotation. We still leave it like that. We don't change the location. You see, it was a right line there, and I left that right line. This one. Yeah, I left that. I didn't mess with that. And then, of course, just so you don't screw up, get rid of the temporary. Okay? So that's the first part of it. The second part of that right-left rotation is now the left rotation. In this case, now we're actually going to perform that on the full thing. So, can this become a cool fade shape? No, it can't. Okay. I'll just highlight it. We're going to do it on that. Okay? So, C, N, O, and it has a line coming from there. We won't mess with that one. That is just going to become that. And then we'll plug it back in. So we have our O, we have our R, and we have the line there. So go ahead and plug it in. And then recalculate our weights. Notice that I don't recalculate the weights in between the two rotations, right? Between the two pieces that I did here. Otherwise, you will find that it didn't help. In fact, it made it worse temporarily. Did it make it worse? No, it didn't make it worse. It just didn't get any better, right? But now it's okay. Oh, I'm missing my little line. That's why. As you can see, that tree, this tree right here, looks much nicer than the one that we had before, which was this one, right? It looks more balanced, right? Look at the height of this. We had 1, 2, 3. Here we only got 1, 2. The smaller the height, the closer it is to log n, then the better, the faster we can insert. Because if we need to insert something into this tree right here, or we need to find something, it's just going to take a worse three comparisons, right? The root comparison, the n comparison, and then either the C or the O in the worst case scenario, right? That big O. In this one, before we did that rotation, it would have taken 1, 2, 3, 4. So one extra comparison, right? One comparison might be a little bit, but so far, I mean, look at this, a small example. Multiply this times like 10,000 ships, now we're talking. So where are we at from Corona? We have to insert the A now. Okay, where's the A gonna go? Well, that's convenient. So recheck the height of the tree and see if it broke. I honestly don't know, but I suspect it may break. No, we'll see. Actually, no, I don't think it will. We'll see. There's a 1. There's a 2. Oh no, it broke on the root. That's the worst ones, right? Because now we actually get to see rotations with children being brought along. I like Karuna is such a nice example. There is the positives of it. See the silver lining. Okay. So where does it break? At the root. That's where we shall perform our rotations. And this is actually the first example where, like, before it was obvious, at least visually, like, oh yeah, that's a double rotation. Oh yeah, that's a left rotation. Oh yeah, that's a right rotation. Here, I don't think it's that obvious. Like, I don't know. I mean, it might be a simple rotation where, like, the n becomes a new root, but we might have to do a double rotation because of the O, for all you know. So we don't know. We're just gonna go with what I told you and hope for the best. So what we do know is that this is where it's breaking, because 3 minus 1, absolute value of that is 2, which 2 is greater than 1, so it breaks there. Don't die. Okay, so let's go ahead and try to perform the rotation that I told you based on the requirement. So we said left or right. The left one is when the right side is heavy, and the right one is when the left side is heavy. So which is the case here? Which side is heavy? The left side is heavy, so that means we are going to perform a right rotation. So this one, okay? So we are going to basically go from that to that, okay? That's the one we're going to try to perform on this thing. So, based on the little algorithm, the n is going to become the new root. In fact, for this one, let's go ahead and copy that actually down, because we want to see where the children are going to end up. And this is the first time that you see it with children. Why is the thing not coming up? How do I, okay, there we go. Okay, so let's identify. Z is our 0, Y is the N, and X is the C, okay? So that means that the N is going to be the new root. What's going to be the X? We said is the C. And then the O is the Z, right? Okay, let's identify which of these are the children. So this is children 4. And this is children 3. This is children 1 here. And then, oh, no. That's children 1. That's children 2 here. So. And then children 4 is that one. And then there's no children 3. Do you concur? Might be easier if we highlight it. There's that, which represents this. And then there is this, which represents that. And maybe we use another color for this one, which represents that one. And then, what color haven't we used? Purple, which represents that one. Okay? Like that. So, all right. Where are the children going to end up then? Well, the children 1 is going to remain on the same spot. So R is going to still stay over here. And then children's 4 and 3 are going to remain in the same spot. We don't have a children 3, but we do have a children 4. So that's going to remain there. And the only one that's going to change places is going to be children 2, right? Children 2 is going to go from being a right child of N, which is now the place of O, and is going to become a left child of Z, which is an O here. So we end up with that. Yes? Okay. Let's check the height. Two. And then was this part of a bigger tree? No, that was it, right? So we fixed it. Yeah, that was it. We didn't have to do like a double rotation. So we are good. We got Corona. Yes, this is Corona. Cool. If we want to make sure we didn't break anything, let's perform the in order traversal of this and see if we get the original thing. Actually, well, no. For this one, can we? No, we can't really get back that original insertion order. Yeah, no, it's lost now forever. Because the binary search inserts wherever it should be sorted. I guess one way that you can check if it's somewhat okay is perform the in-order traversal and see if it's sorted. So the in-order traversal of this is A, C, N, O, O, R. That is in ascending order, which at least tells us that the binary search tree is still a binary search tree, which is a good sign. So I guess a combination of that and the fact that we have a log n height. So how many nodes do we have now? We have 2, 4, 6 nodes. Again, we said that's about 3. We have that height, so that's close enough. So that means that both the height of the tree is log n and it is in sorted order, as the in-order traversal is sorted. So that tells us that everything seems to be okay, which is ultimately what we're trying to do. Okay. We still have 5 minutes, so let's just keep inserting things here. Let's try to break it more. Let's insert a B into it. Or does anybody have any questions, though, so far? How do you feel about AVL trees in general? It's a little bit tricky. Yeah.
For these numbers, you're getting like the heaviness on each side. Is it like a function like get height for just this right side, or is it like the number of recursive calls on that side?
Get height will get you the right values, I suppose. Yes.
Like when we implement it.
When you implement it,
will that get
you
height?
can use get height, yes.
Okay.
To make things easier, I would add to the class a left height and a right height count to also keep track of that, because that way your code is more efficient. Otherwise, it's like trying to do Fibonacci, and every time you measure a Fibonacci number, you're measuring the entire Fibonacci tree, when you can use dynamic programming to remember that. So, yes, I would do that instead of just grind. I mean, you could, but 10,000 ships, Sally, recursion, things might get nasty with it. So, yes. Let's add a B to this. So, B would go there. Actually, before I add B, we talked about inserting, but how do you delete? Deleting is the same thing. You, if you say you want to delete R, or actually let's try to delete G, first of all. What's the process of deleting G? You start out at the end, you say, is G less than N? Yes, right? C. Okay, is G less than C? No, G is greater than C, right? So you go here and you're like, well, there's no child there. At that point, you can return to the user and say, G was not found in the tree, so we deleted nothing. Okay, cool. Now try to delete R. Delete R, gets to the R end here, bigger than that, so it checks with the O. It's bigger than the O, finds the R. It's like, oh, perfect. Okay, let's go ahead and kill that. All right. In this case, you just delete it. And after you delete it, what you go ahead and do is you go ahead and recheck the height of that section of the tree to make sure that when you deleted it, it didn't make it unbalanced, because there is a possibility that it would have made it unbalanced. In this case, 1 and 0, 2, everything is still balanced. How could I have made something unbalanced? Well, in this case, if I delete one of the O's, if I delete this O, then this becomes a 0, and it's still balanced. Okay, delete the other row. Now it's unbalanced. So it's possible that your tree may get unbalanced if you delete enough nodes. Sometimes it's a single node that's holding it balanced. And when you delete that, it breaks the entire tree. In fact, it's not really visible here, but like suppose we had another node here. Suppose we had a Z. And you go ahead and you delete the R. Well, is it balanced like this already? Yeah, it is balanced like this, because this is a 1 here, and this is a 2 here, and then this is a 3 here, so it is balanced. Perfect. So now here, suppose you delete actually the A. If you delete the A here, this becomes a 0, this becomes a 1. So yeah, look at that. Deleting the A just broke the entire tree. So that can happen. I guess, yeah, why not? Let's fix that.
I'm fine with it broken.
What's that?
I'm fine with it broken.
You fine with it broken? I mean, we do have like 2 minutes left. But you would try to rotate over here, make this, I'll just speed up that way, and then keep the children in the right spots. The O is the only one that gets moved over here. And there you go. It has been fixed. I think it has been fixed. Did we lose any letters? No. 246. 246, yeah. Okay, there you go. So all I had to do was perform, what is that? It's, name-wise, I get them flipped. Left rotation. The other case, last thing that I want to tell you is if you have a tree like this. So suppose you have back to this tree, okay? Suppose that you go ahead and you delete this one. Maybe it was a different letter. Okay, suppose it was what's after N? Q? No. Oh, dang it. Well, let's say it was an O here, and then we had say it was a P here, and maybe we have an O here. Okay? If you delete the P, who do you replace that with? You replace that with the rightmost item that is left of what you just deleted. So you go left here, and you traverse this until you find the rightmost thing, and then you replace that. If there is no left child here, then you simply take the right child and make that the parent, as such as this would be the case here if there was no O. The rightmost thing here also happens to be the previous item in the in-order traversal. So that's what you do. Although in the assignment, I don't make you code delete, you should know that because it might be on the test. Okay, well that is AVL trees, so now you should be able to do assignment A. We will still talk more about AVL trees next class, but your assignment will still be due on the date it's due. We'll just kind of refresh it because we have the whole spring break in between. So happy spring break, I suppose. I'll be on Discord if you need help. Thanks for watching.